Hello everyone. In this session, we are going to discuss the further part of unit number 3, that is nothing but the hysteresis. Now, the hysteresis is nothing but the curve or the magnetization curve, which is a graphical representation between the magnetic flux density and the magnetic field. Now, hysteresis refers to the lagging of the magnetization of a ferromagnetic material like iron. In other words, when a ferromagnetic material is magnetized in one direction, it will not relax back to zero magnetization even when the imposed magnetizing field is removed. Hence, it has to be driven back to zero. A field in the opposite directions needed to be applied. If an alternating magnetic field is applied to the material, its magnetizations will trace out a loop called a hysteresis loop or BH curve. The study is well supported by the West domain theory. According to the West domain theory, the hysteresis is nothing but the lagging of the magnetizations of a ferromagnetic material like iron. The behavior of that magnetizations, which is nothing but the lagging concept. Lagging means it should be far behind of a particular value. In other words, when a ferromagnetic material is magnetized in one direction, it will not relax back to a zero value even when it is imposed the magnetizing field is removed. And according to that, when an alternating magnetic field is applied to the material, its magnetizations will trace out a loop called as a hysteresis loop or BH curve. Also, we can call as the magnetization curve of ferromagnetic material. Now, this is nothing but the magnetization curve or hysteresis loop. As shown in the figure, the magnetization curve is divided into 4 regions. In the region where, or in this figure, we have classified or we have represented this image or slide with the help of magnetizing force, that is nothing but H, and the flux density, that is nothing but capital B. In the x-axis, we have magnetizing force either in positive directions or in opposite directions. We have to be considered, that is nothing but the negative H, whereas the flux density should be represented with the help of capital B, which is represented on y-axis, whereas the minus B represents the flux density in opposite direction. Now, when any magnetic material is having placed into the magnetizing or magnetic material, then the moment of that particular magnetic moments is represented at the origin. Means over here in the dotted line, the value of external field it should be a small, that is nothing but H is small, and the domain wheel movements are mostly irreversible. This corresponds to the known reversibility of initial portion of the magnetization curve. The behavior it should be starts from 0 and it should be goes on upward direction up to the saturation point, that is nothing but at point A. In the region where the field values are going to the higher one, and also the domain of that magnetizing field or magnetizing force goes to the upward directions with the help of flux density, and it should be reaches at a particular value, that is nothing but A, where the point at which now over here the magnetizing force is not go to the increasing level, as the flux density of that particular parameter it should be goes on increasing level. Okay, so this is the highest value where the magnetizing force of that particular material it should be stops, or it should be end over here. At that point, if we increase the flux density over here, then also the magnetizing force it will not be goes on increasing level. So now we are reducing the magnetic flux density towards 0. Then that particular parameter, that is nothing but the magnetizing force, it should be take the path, that is nothing but from A to B. Means as we reduce the flux density of that particular material, then the magnetizing force goes on reducing level up to part B. So this is the reverse effect which should be produced by that material, that is the path or the distance between A to B is nothing but the reverse effect of that magnetizing force as we decrease the flux density of material. Now from B to C, as we decrease the flux density up to the lowest value, the distance should be covered from B to C. Now the magnetizing force which are generally start at that origin level, but it comes under the new circumstances, that is the magnetic force becomes that negative value, means it should be having the opposite direction, the region over here, and it should be introduces the coercivity of that material. Now as we decrease again the flux density towards a negative side, that means in opposite direction, then we can get the saturation in opposite direction. Means as the D approaches or D reaches, if you decrease the flux density furthermore in this downward direction, then also the magnetizing force created by that particular material it should be same. Now if we increase againly the flux density from here, then instead of starting that magnetizing curve or flux density from that origin, it should be starts with the negative saturation level to the positive saturation level, as it should be takes a path of small d, E, F and A. So over here it should be creates a new path when we can increase the flux density of that particular material. So this is how and BH curve it should be identified or it should be processed. As the process of domain rotation is difficult, the rate of increase of magnetization slows down with the region of the particular curve. The hysteresis effect observed in a magnetization curve is due to the irreversible domain movement and rotation. So we can take the description of that hysteresis loop. On application of magnetic field on a ferromagnetic material, it shows a non-linear rise, that is, flux density lags behind the applied external field called as hysteresis, which is plotted along a y-axis. The material reached saturation as all the domains align parallel to the applied field on removing the applied field H is equal to 0. Some of the domains retain their alignment, resulting in a residual magnetism. This loss of retraceability results as the hysteresis loop as shown. The residual magnetic field, called as retentivity, which arises as many of the domains retain their alignment along the direction of the external field that was applied. Its value is given by the y-intercept. Now, an external magnetic field is applied in opposite direction so that the residual magnetism gets reduced to 0. This value of the field is called as coercivity. This term specifies the hardness or softness of the material towards magnetization. The hard materials like steel have high value of, while the soft materials like soft iron have the low value of coercivity. Over here we can define a specific definitions regarding with the BH curve. The applied magnetic field strength is further increased in the reverse direction till again saturation is reached by the alignment of all the domains along the direction of applied magnetic field H. The process of reducing the applied field to 0 followed, and again the applied field is increased in forward direction. The said process is repeated by constantly changing the direction of applied magnetic field by changing the direction of the AC supply to the coil. Magnetic hysteresis loop or BH loop is obtained. The BH loop gives us the magnetizing behavior of given ferromagnetic material. The above process involves loss of energy in the form of heat, which is proportional to the area of BH loop. The greater the area, better magnetism produced, and vice versa. As given below, there are the representations of soft iron and hard ferromagnetic materials. Again, we have repeated this part because this should be having the more importance in that concept. Now over here, the magnetic hysteresis or hysteresis loop, it should be having the four main steps. The first one is that increase in the current in the position in a positive direction in a suitable steps. For each value of I, the B should be changes and H should be changes. That is nothing but the first step should be starting from origin, where the X and Y axis should be crossed each other to the, we can mention that point, that is nothing but 0. From 0 to A, the first process should be there. Second one, now decrease the positive current in a suitable steps up to the 0, and for each value of current we have to be find the B and H. That is nothing but from saturation point we have reduces the value of flux density up to the negative saturation is to be obtained. Now again, increase the current in a negative direction in suitable steps to plot the points. And finally, fourth step is what? So finally decrease the negative current to 0 and plot the points. Now if we follow this procedure, we can get a particular hysteresis along with the direction. Now in this parameter, we have different types of new concepts, that is nothing but the retentivity or residual magnetism. The definition of that retentivity or residual magnetism is that the residual flux density is also called as the remnant flux density. This is the property of magnetic material which can retain their residual magnetism, called as retentivity. Next point is nothing but the coercive force should be indicated by coercivity. The value of magnetic field strength required to wipe out the residual flux density is called the coercive force. The process of reducing the magnetic flux density B to 0 is called as demagnetization of the core. Again, we have to be define that coercivity. The value of magnetic field strength required to wipe out the residual flux density is called as the coercive force. It should be indicated by capital HC. In this, the magnitude of residual magnetism and the coercive force depends on the imperfections in the material, such as voids, impurities, and internal strains. In fact, the coercive force comes into existence due to all these imperfections because the energy that is required to move a domain over an imperfection. So, if a material has large internal stresses and non-magnetic inclusions, then the coercive force will be large. The value of desaturation, that is the saturation of flux density, depends upon the chemical constitution and the temperature, and does not depend upon the imperfections. The hysteresis loop usually shows the hysteresis loss also. Due to the presence of magnetic hysteresis, a fraction of applied power will be lost in the form of heat. The portion of a power lost corresponds to the difference between the energy stored and the energy returned by the magnetic core. This is called as the hysteresis loss, which are mainly depends upon the frequency of magnetization, the area enclosed by the hysteresis loop, and the volume of that material. Over here, from that diagram, we have to be defined, that is soft magnetic core or soft magnetic material or hard magnetic material. The BH curve, it should be introduces, or it should be gives us the information of magnetization or the BH curve, which is called as the hysteresis curve also. Now, those ferromagnetic materials have a small area as energy loss over BH curve is called as soft magnetic materials. Soft magnetic materials can be defined as those ferromagnetic materials having a small area as energy loss over BH curve is small. If the area of that energy loss should be a smaller one, then we have to be called as BH curve also creates a smaller portion over there in the form of coercive force, and we can define that material, that is soft magnetic materials. Whereas those ferromagnetic materials have a large area as energy loss over BH curve is large. This form of magnets are good for magnetic materials. If the BH curve having a large coercive force between B and H, then that type of material we can call as hard magnetic materials, and this form of magnets are good for magnetic purposes or magnetic applications. Next one, that is nothing but the magnetostriction effect. The magnetostriction is a property of ferromagnetic material that causes them to change their shape when subjected to the magnetic field. Also, this should be defined as the phenomenon in which there are small changes in the dimension of ferromagnetic substance when it magnetized is known as magnetostriction effect. The effect first identified in 1842 by James Joule when observing a sample of nickel. This effect can cause losses due to the frictional heating in the susceptible ferromagnetic cores. We have another property of magnetic material, that is nothing but magnetoelastic coupling. In that one, the magnetoelastic coupling is nothing but the interaction between the magnetization and the strain of magnetic material. We can call it as magnetoelastic coupling. Okay, let's discuss this magnetostation effect with the help of diagram. That is nothing but when in the absence of a magnetic field, the magnetic dipoles are present in a tail-pull D bar. In the particular section of that bar, the magnetic dipole moments are available in a dispersed manner. But when these are the magnetic dipoles which are in the first bar, the magnetic dipole moments are dispersed with each other in the absence of magnetic field. But when the magnetic excitation it is to be placed between that bar, the magnetic dipoles are having the superposed position with the same polarity of that magnetic dipole. Then the magnetic dipole directions, they are placed in a one particular direction at that magnetic field it is to be applied on that particular material. Now this type of magnetostriction effect is available over here. We can define the magnetostriction coefficient that should be indicated by lambda as the increase in length per unit length of crystal in the direction of magnetization. Now the figure shows the magnetostriction coefficient, that should be nothing but the lambda for a ferromagnetic material like iron with respect to the magnetization M. That we define that the iron crystals expand when the magnetization in the easy direction of magnetization and contract when magnetized in the hard direction. Over here, the direction of that magnetic field is more important. The magnetic permeability is dependent on the magnetostriction effect. In fact, the magnetostriction effect should be minimized in order to obtain higher values of permeability. So here some discussed points regarding with the magnetostriction effect. The magnetostriction is a phenomenon observed in all ferromagnetic materials. It couples elastic, electric, magnetic, and in some situations also thermal fields, and is of great industrial interest for use in sensors, actuators, adaptive or fundamental structures, robotics, transducers, and MEMS, that is nothing but micro-electromechanical systems. The magnetostrictive material develops large mechanical deformations when subjected to an external magnetic field. This phenomenon is attributed to the rotations of small magnetic domains in the material, which are randomly oriented when the material is not exposed to a magnetic field. The orientation of these small domains by the imposition of the magnetic fields creates a strain field. As the intensity of the magnetic field is increased, more and more magnetic domains orient themselves so that their principles axis of an isotropy are collinear. So with the magnetic field in each region, and finally saturation is obtained. The magnetostriction or Joule magnetostriction is a consequence of the magnetoelastic coupling. It pertains to the strain produced along the field direction and is the most commonly used magnetostrictive effect. The Joule magnetostriction is the coupling between the magnetic and elastic regimes in the magnetostrictive material. The magnetostriction is an intrinsic property of magnetic materials. So over here, the magnetostriction effect is to be defined, that is one circular bar having the magnetic field, that is nothing but H, is wounded along with the current or the wire in which the current I should be flows from there. The length of that conductor should be nothing but L, and when the current E should be introduced to that particular bar, it should be changes its length from L to L plus delta L. Now the change in that particular material is mainly depends upon the magnetic field introduced to a particular material. When the current it should be introduced in that particular material, then it should be creates a magnetostriction effect. Due to that, the length of that conductor or the length of that particular material it should be changes. It should be creates an delta L effect over here. Because of that, the H and delta L upon L, that is nothing but the change in length to the length is to be introduced over here. According to that, the magnetostriction effect is to be understood. The next point is nothing but the permeability, which should be denoted by mu. The permeability of magnetic material is a measure of the ease in the magnetizing material. Permeability of magnetic material is a measure of the ease in magnetizing the material. The permeability mu is the ratio of flux density V to the magnetizing force H. Mu is equal to V upon H. That should be nothing but the permeability of material. The relationship between V and H is non-linear. That means the relation between flux density V and magnetizing force H is non-linear, as shown in the hysteresis loop in the figure. Then it is evident that the ratio of V upon H, that is nothing but the permeability, also varies. The variation of permeability with flux density V is shown in the figure. Also, it shows the flux density at which the permeability is at maximum. Now, the next point is nothing but the factors affecting permeability and hysteresis loss. The permeability mainly depends on the physical condition and the purity of the magnetic material. The permeability decreases due to the cold working of the material. The material whose permeability has decreased due to cold work can be heated up to restore its magnetic properties again. The maximum value of permeability obtainable for a material is limited by the impurity content of the material. Typically, the impurities are carbon, sulfur, oxygen, and nitrogen. Out of these, the carbon has the worst effect on permeability, so the amount of carbon is kept as low as possible. That means it should be kept 0.01% of the material. So these are some parameters which are generally affects the permeability and hysteresis loss of material. As mentioned over here, the permeability should be depends upon the physical conditions and the purity of the material. The permeability also depends upon the cold working. The material whose permeability has decreased due to cold work can be heated up and restore its magnetic properties again. The maximum value of permeability obtainable for a material is limited by impurity content of the material. With such impurities, that carbon, sulfur, oxygen and nitrogen, the carbon has the worst effect on permeability, so that the amount of carbon should be kept as low as possible. In general material, it should be kept 0.01% to the magnetic material. So up to this part, we have ended over here. For any queries or questions, kindly message or convey the questions towards me, so I will resolve that questions and you will take the further part of this unit. Okay, thank you.